Welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we also see and appreciate the beauty in the simpler problems. So today's problem comes from the MIT 2022 Integration B, quarterfinals number 2, problem number 3. And we'd like to bunch this problem into the category of limits. So our problem is the limit of n tending to infinity, the nth root of the integral from x equals to 0 to 2 of 1 plus 6x minus 7x squared plus 4x cubed minus x to the power 4 all to the power n. So it's a very interesting problem. But before I jump into the solution, I'd like to first of all shout out to our subscribers. Thank you so much for the support you've given us. It's been really amazing, the support you directed towards us. We don't take that support for granted, and it's your support that motivates us to come here time and again. Now, for our first-time visitors, just a quick spiel of what we do here at Everyday Mathematics. What we do is we go out there, we look for very hard problems, and we come back and we share with you the solutions that we propose would be apt for them. And then for repeating visitors, please, we do request of you to pause the video and subscribe to our channel. For your support will do a lot in giving us the extra visibility that we need. So looking at the solution for this problem, first thing is we need to rearrange the integrand a little bit. And how we would go about doing that is we would like to, first of all, hone down on the x to the power 4 term. And we can see that there is, and also this for the power x power 3. So these could be bunched into the x to the x minus 1 to the power 4 expression. And so what we have in bracket here is x minus 1 to the power 4. And because we have this 1 that we've taken here, we've added a 1 here. And so we could also now pick out the x to the x minus 1 to the power 2 or x minus 1 squared and bunch it in the bracket we see here. And so we're left with 3 here. So eventually we have an expression 3 minus x minus 1 squared minus x minus 1 to the power 4. Okay, so our limit and integral can now be re-expressed or represented as the limit as n tending to infinity of the nth root of the integral from x equals 0 to 2 or 3 minus x minus 1 squared minus x minus 1 to the power 4 to the power n. So the next thing I'd like to do now is to substitute for x minus 1. And how we do that, we say let u be equals to x minus 1. Such that we really simplify this a little bit further, so that du dx is equals to 1, and therefore du is equals to dx, right? And so the limit also changes when x equals to 0, u is equals to -1, and when x equals to 2, u is equals to 1. So this is what now our results, okay? And so we've done all these. And so since the absolute value of u is less than 1, what that really means is that the integrand now we have here under the nth power here is greater than 3 minus u squared, 3 minus 3u squared, but is also less than 3, right? And so we can now use what some people call the squeeze theorem. And what happens is we can now say, okay, we have our integral in between the limit and integral of the limits we just created previously, right? So on the upper side, we have the limit of the nth root of the integral from u equals to -1 to 1 of the power n. Since this is a constant, we can pull this out. And so after pulling that out, the nth root of 3 to the power n is just 3. So we can pull that and we have 3 here. And now we're left with the nth root of the integral from u equals to 1 to 1 of 1. And since this is u, we apologize for that. This is u. Let me use a better eraser here. So this is u. And this is also 1. So we have 1 minus negative 1 is equals to 2. And this, since you say this is u, this is 1. So we're left with the limit of the nth root of 2. And we can express this as 2 to the power 1 over 2 to the power 1 over n. And if n tends to infinity, what it means is that this tends to 0, right? And so we're left with 3 times 1, because any number to the power 0 is 1, and that is the upper limit. Right? So the next thing we would like to do is focus on the lower limit. And what I would do is substitute for u with a trigonometrical function. And that is, we could use sine theta. But even before that, let's pull out the 3. And as you can see, again, 3 is a constant here. Pull it out here, and that becomes 3 to the power n. And the nth root of that is 3. So we have 3, the limit of n tending to infinity of the nth root of the integral from u is equals to negative 1 to u is equals to 1 of 1 minus u squared. So we can now replace this with sine theta. So letting u be cosine theta, that means that du d theta is cosine theta. And so du can be replaced with cosine theta d theta. Looking at the limits, when u equals to negative 1, that means that sine theta is equals to negative 1. And so what that essentially means is theta is equals to negative pi over 2 when u is equals to 1. That means also that sine theta is equals to 1, and therefore theta is equals to pi over 2. So substituting that in, we have 3 limit n tending to infinity of the nth root of the integral of 1 minus sine square theta to the power n cosine theta. So this expression here is the same as cosine theta, just using the identity sine square theta plus cosine square theta equals to 1. And so eventually we have now the integral under the limit and the nth root sine of cosine to the power n theta to the power 2n theta cosine theta. So let's try to integrate this. We can do a number of things focusing on this integral. Let's focus on that. So we can let our u to be cosine to the power 2n theta, and our dv be equal to cosine theta. What that means is that our du, differentiating this, is negative 2n cosine to the power 2n minus 1 theta sine theta, and our v is sine theta. So using if u dv is equals to uv minus v du, this is obviously integration by parts. That means that our integral here is the same as this integrated, and we have our limits applied. And as we can see, if we apply pi over 2 here, cosine of pi over 2 negative is 0. Cosine of pi over 2 positive is also 0. So this term here just tends to 0. Times, okay, here the negative here becomes positive because of this. And so we have 2n integrating v du, or v sine theta, and then du is cosine 2 minus 1 theta sine theta. So we have sine square theta there. And so eventually what happens here is that since we've agree that this term tends to 0, we are left with just the 2n times the integral from theta is equals to pi over 2, negative pi over 2 to pi over 2. And this is sine squared, so we can convert this to 1 minus cosine squared theta by plugging that in. And eventually, we do have cosine 2n minus 1 theta integrated minus 2n, again the same integral, cosine 2 to the power n cosine theta. So we see that this here is the same as this here, so we can take this back to the left hand side, and what happens is now we have 2n plus 1 cosine 2n, the integral cosine to the power cosine to 2n theta cosine theta is equals to 2n, the integral of cosine 2n cosine to the power n minus 1 theta. And so we can divide both sides by 2n plus 1, and so our integral now becomes 2n over 2n plus 1 cosine to the power 2n minus 1 theta. And see, this process can repeat itself again. And so we do essentially have a recursive process going on here, since the integral cosine 2n minus 1 is the same as 2n minus 2, 2n minus over 2n minus 1, the integral of cosine to the power 2n minus 3, and that process continues. So essentially, as I mentioned, we do have this integral being 2n over 2n plus 1 times 2n minus 2 over 2n minus 1, the integration of cosine 2n minus 3. And so this here, believe you me, gentlemen and ladies, is a recursive process all the way to the integral of cosine theta. And this obviously is sine theta, and the integration of sine, the integral of cosine theta with this limit results into a value of 2. And so we can now conclusively say that our result there is all this all the way times 2. Now, as you can see, this is interesting, because if we pull the 2's out, we have a process where we're multiplying n times n minus 1 all the way to 1 at the denominator, replacing this part here. And then here, as you can see, we do have the odd values of this. And so if we have 2 times of this, if we square this, then we have 1 term replacing this, because in order to come back to this expression, then we'd have to substitute a similar value up here, and that plugs in the gaps we have here. So essentially, 2n plus 1, see, we have this, we have another here, and obviously 2 at the end here. So this becomes 2n plus 1 factorial. So by pulling 2, as I mentioned previously, we have 2 to the power 2n. And then here we have n factorial squared over 2n plus 1. And that is that. So now, because we had a square root, nth root, sign over the integral, we can now pull out this 2 to the power 2n, because the nth root of this is just 2 squared. And then we can also pull this out into 2 to the power 1 over n. So focusing on that, we say let k be equal to this remaining part here. That's kind of nebulous because I want to figure out what is the limit of this value as n tends to infinity. So k to the power n is n factorial squared over 2n plus 1 factorial. And therefore, taking the logs, natural logarithm of both sides. So now we have n, natural logarithm of k is the same as 2, pulling 2 out of the summation, log 1 plus log 2 plus, because the product, when you take the log of products, the same as the sum of the specific, the logs of the independent parts. And minus anything in the denominator, so we have log 1 all the way to 2n plus 1. Okay, so dividing both sides by n, we have log k, 2 times 1 over n, log 1 plus log 2 plus log n minus 1 over n, log 1, summed all the way to log 2n plus 1. Okay, so eventually, 1 over n log 1 up to n, since the extra one cancels the values here of 1 to n. And so now we have minus 1 over n times log n plus 1, n plus 2 all the way to 2n plus 1. Now we can batch this with this and this with this in such a way that now we have 1 over n log 1 over n plus 1 plus log 2 over n plus 2 and so on until you have log n over 2n or log n over 2 over n plus n. Okay, so using the summation sign, we have 1 over n summation of from k equals to 1 to n of logarithm of k over n plus k. Okay, minus 1 over n log 2n plus 1. So this is just the residual term there. And so pulling out the n and the k, we have, this is the same as the summation from k equals to 1 to n of the log of k over n times 1 over 1 plus k over n. So the interesting part here comes that the limit of n tending to infinity of log k is the same as n tending to infinity of 1 over n, the summation here. And as you can see, as n tends to a very small value, now we have the Riemann definition of an integration. And so that means that we can take this to be our x, and this to be our x, and this to be our dx, the small dx, because when n tends to infinity, this becomes very small value. And so this is the same as the integration of log x times 1 over 1 plus x from 0 to 1 minus, since we see that this bulges more than the logarithm of 2n plus 1. In other words, this increases way more than the numerator. This here just simply tends to 0. We can spend time here to show how that happens, but it's an obvious, it's a very trivial problem. So now we have the integral of log x minus log 1 plus x from x equals to 0 to 1. So the integral of log x, we can take our du to be 1, and then our or u to be 1 and dv log x, so that now our uv is x log x with the limits obviously minus, then we have our u, I mean dv, du, dv is x times 1 over x, because the derivative of log x 1 over x. So this and that cancels. So we have the integral of 1. And then the same thing would happen here. So we have x log x plus 1 from 0 to 1. And obviously minus x times 1 over x. 1 plus x, sorry. So this one tends to 0 because log of 1 is 0. X here is 0 and 0. So this is 0. And this here, 1 minus 0 becomes We just leave it there for now. But we can divide this numerator by the denominator, and the same as 1 minus 1 over x plus 1. And if we integrate this separately, this and that cancel, so we're left with the integral of 1 over x, 1 over x plus 1 minus log of here. Okay, so eventually we have the integral of log x plus 1, the x plus 1 with the limit 0 to 1. And so this is the same as negative log 2 minus log 2, which is the same as minus 2 log 2, and taking 2 out, it becomes 2 to the power 2, so it's log 4. Okay, so the limit of log k is equals to negative log 4, which is the same as log of 1 over 4, because negative 1 going into the power there means that we have a quarter. So one thing that can be done is now we can plug this k back into our integrand, because previously we said our lower limit is 3 times the limit of n tending to infinity of the nth root of the integral of this cosine to the power 2n theta cosine theta, and that is the same as the limit of 2 times 2 to the power 2n n factorial squared over 2n plus 1 factorial, basically nth root there. And so we already pulled out, and we thought that this is 2 squared. We pull these things out, and then limit n to infinity of 2 to the power 1 over n. And here, this one tends to 0 if n tends to infinity. And so 2 to the power 0 means that we have a 1 here. But we also found that since this was the k value tended to a quarter. And so since this is 4, a quarter, this and that cancelled, we leave with 1, and eventually we have this remaining, and we know this tends to 1, and so we have our integral and limit finally really beautifully sandwiched between 3. So what this really tells us is that the limit of n tending to infinity of the nth root of this integral 0 to 2, or 1 plus 6x minus 7x squared plus 4x cubed minus x to the power 4 to the power n is 3. And this is our answer. Really beautiful. It's really wonderful walking through, but yeah, it was a beautiful solution. Thank you so much for following along with us. We're growing. Our channel is really picking a lot of interest, and so if you want to walk with us, if you want to move along with us on this journey, please subscribe to our channel, and we promise you we'll be coming back to you with some very interesting solution. Thank you so much. Until next time, may you have a wonderful year ahead. Thank you.